Welcome to an overview of Amazon SageMaker. Amazon SageMaker is a fully managed service that provides developers and data scientists with the ability to collect and prepare, build, train, and deploy machine learning models quickly. Amazon SageMaker removes the heavy lifting from each step of the machine learning process to make it easier to develop high-quality models. Amazon SageMaker provides all of the components used for machine learning in a single toolset, so models get to production faster, with much less effort, and at a lower cost. Here are some of the benefits of using Amazon SageMaker. Make machine learning more accessible. With Amazon SageMaker, machine learning becomes more accessible, enabling people to innovate with ML through a choice of tools, an integrated IDE, and no-code visual interfaces. Prepare data at scale. With Amazon SageMaker, you can access, label, and process large amounts of structured data, like tabular data from spreadsheets, and unstructured data, like photos, video, and audio. Accelerate ML development. With Amazon SageMaker, you can reduce training time from hours to minutes with an optimized infrastructure, and you can boost productivity with purpose-built tools. Amazon SageMaker also enables you to automate and standardize MLOps practices across your organization, allowing you to train and deploy models at scale. Amazon SageMaker can be utilized for specific use cases as well. With Amazon SageMaker Canvas, business analysts can easily prepare data, train models, and generate predictions using a point-and-click interface. They can then share the results with data scientists and integrate them into common business intelligence tools. With Amazon SageMaker Studio Notebook, data scientists can access data from structured and unstructured data sources, improve productivity with purpose-built tools, and fully manage Jupyter notebooks with just a few clicks. And with Amazon SageMaker MLOps, software developers can build CI/CD pipelines to reduce model management overhead, automate ML workflows to accelerate data preparation and model building, training, and experiments. They can also monitor ML model quality by automatically detecting bias and drift, and automatically track code datasets and artifacts at each step of the ML lifecycle. Machine learning overview. Machine learning, or ML, is the process of teaching a machine or a computer how to perform a task such as identifying fraudulent credit card transactions. Before machine learning, using classical programming, developers spent many hours creating logic rules and applying them to a specific data set to calculate an answer. Now with machine learning, developers can create computer algorithms that can learn from experience without relying on rules-based programming, thereby moving the heavy lifting away from humans and onto machines. Machine learning is good at solving problems, like predicting the price of a book based on its features, such as the number of pages, the author, and whether it has a hardcover or not. It also excels at solving classification problems like determining whether a movie review is positive or negative. Machine learning components. Data. The data to solve a machine learning task consists of features and a label. Feature data are the inputs, or X variable, the known attributes about the problem your task is trying to solve. Label data is the output, or Y variable, the value or attribute you are trying to predict. ML data types can be either categorical such as a movie genre, or numerical such as a book price. Algorithms. A machine learning algorithm is a set of instructions a computer runs to determine the rules that allow it to predict a label or output in a dataset. There are two types of machine learning algorithms. Supervised ML algorithms use data with labels, or the observed output, already included with the feature data. Supervised ML algorithms are suited for solving problems involving linear regression and classification. With unsupervised ML, the labels are not provided as part of the input. Unsupervised ML algorithms are better at solving clustering problems that find naturally occurring groupings. Machine learning lifecycle. The machine learning lifecycle involves determining the business problem with goals that are specific and measurable. Defining the machine learning model by rephrasing the problem using ML terminology, and then identifying the type of algorithm that is best suited for the task. The next step is to prepare the data, which requires gathering, merging, and cleaning up features and label data. Once the data is ready, you train and test the model, and tune hyperparameters until the desired accuracy is achieved. The final step is to deploy the model to production, and then evaluate it to improve the predictions by iterating over the previous steps. Machine learning algorithms. Machine learning, or ML, can help solve a variety of business problems across many industries. An example of questions that ML can help a data scientist answer are: is this internet traffic pattern indicative of a hacker? Does this mammography scan show signs of cancer? Or, how many days before this manufacturing part fails? A data scientist must choose the type of ML algorithm to use. This decision is mostly dependent on the type of data available to train the model. If the training data includes both features and labels already defined, then you can use a supervised learning algorithm. If the training data does not include labels, then you would use an unsupervised learning algorithm. Let us take a closer look at both types of algorithms. Supervised algorithms. Linear regression. Linear regression algorithms aim to learn the correlation between a set of input features X and a continuous output variable Y. The goal of the algorithm is to be able to predict a continuous numerical value. For example, a manufacturing engineer, knowing the number of weeks before a critical component fails, is valuable, allowing them to proactively schedule focused maintenance, thereby reducing downtime. Classification. A classification algorithm's goal is to understand the relationship between feature data and an output label. The end result should be the ability of the ML model to separate the data into distinct groups. For instance, to predict customer sentiment, a company can collect data such as age, gender, purchase history, and customer service interactions. The ML model can then use that data to compare how other customers with similar features felt, and then label their sentiment as happy or not happy. Unsupervised algorithms. Clustering. Clustering algorithms analyze unordered input data and attempts to label them into discrete groupings. In this case, the unordered items have been analyzed and labeled into 3 groups: fish, sheep, and cats. The number of groupings and the group labels are unknown and part of the problem the ML model solves. For example, a clustering algorithm can be used to determine what trending subjects are being discussed in an organization's social media posts. Then cluster them into topics such as an upcoming merger, a new product launch, or a service outage, so they can be addressed by management. Anomaly detection. Anomaly detection algorithms help solve a special type of ML problem where the number of clusters is 2. This type of algorithm excels at finding unusual activity in large datasets. Detecting intruders in a computer network by analyzing log data is an anomaly detection problem. Unusual activity would be labeled as anomalous if it departed significantly from normal patterns.